All right, here for the notes for section 6.2, which deals with definite integrals. So two objectives: express the area under the curve and then compute the area using numerical integration procedure. So we start by talking about what a Riemann sum is. So being some arbitrary continuous function, so that's this lovely curve, on some closed interval from A to B. We then partition the interval from A to B into n subintervals by choosing n minus 1 points. So for example, if you want to choose 6 subintervals, you choose 5 values because you'll have the extra one at the end between A and B. So here's your restrictions. So A is the smallest number. They count up until you get to B, the largest value. To make the notation consistent, we denote A as x0 because x1 is the smallest value here. So A becomes x0 and B becomes xn. The set P is the list of these numbers. It's called the partition of A to B. So the partition denotes n closed subintervals. So if the full interval is A to B, if I start dropping values in here, I get subintervals, smaller intervals. In each subinterval, we select some number, denote that number from the kth interval by C of k. So this is kind of like from the last section where we chose either the middle, the left, or the right when you were doing MRAM, MRAM, RRAM, and LRAM. So then, on each subinterval, we stand a vertical rectangle, so as you see here, that reaches from the x-axis to touch the curve at some point. So here's our value, it touches the curve here, so this one would be an L. This one they used M, M. If you notice though, they're not consistent where the rectangle touches the curve. You just go up essentially until the vertical height is where you have it to be. So your C value determines how tall your rectangle is. If C is on the left edge, it's the left, it's in the middle, but it could be some odd thing like here where that's the C value for this interval is not left or right or middle, it's slightly to the right. So in each subinterval, we form the product f of ck, so that's the height of the rectangle, because f of c is the y value, and then delta x is the width of the interval. So that's how you find the area of a rectangle. This product can be positive, it's above the x-axis. It can be negative if it's below the x-axis, or 0 if the rectangle has no height, which we don't have any examples of here, I suppose. Finally, we take the sums of these rectangles, which is what we did when we did the accumulation problems from, or we did RRAM and so on and so forth last section. This is referred to as a Riemann sum. So all Riemann sums for a given function on A to B converge to a common value, as long as the lengths of the subintervals tend to 0. This latter condition is asserted by requiring the longest subinterval length, called the norm, to tend to 0. So what that means is, as these rectangles get narrower and narrower, all the options you choose will eventually reach the same value. So which is why when you're doing MRAM, RRAM, and LRAM last section, the more intervals we had chosen, the closer those values would come to each other. Okay. We don't have an example yet. Okay, so just some definitions. The definite integral as the limit of Riemann sums, so let f be a function defined on a closed interval from A to B. For any partition of A to B, let the number ck be chosen arbitrarily in the subinterval, which means they don't have to be on the left, on the right, or in the middle, just anywhere in, as long as they're in between these two values. If there exists such a number I, such that so remember, this is the width of the subintervals. So if the widths tend to 0, you start with the first subinterval up to the last one, height times width, so that's the area of the rectangle, it'll equal some value I. No matter how the p's and the c of k's are chosen, then f is integrable on A to B, and I is the definite integral of f over A to B. So all continuous functions are integrable, meaning you can take their integral. That is, if a function f is continuous, then its definite interval over A to B exists. Since we know for all continuous functions the Riemann sums tend to the same limit for all partitions, we only need to consider the limit of so-called regular partitions, in which all subintervals have the same length. The previous thing we were talking before, you could make those rectangles. The first one could be 2 units wide, the next one could be 1 unit wide, the third one could be 3 units wide, so on and so forth. But it's easier if you just make them regular, meaning each thing is the same width. From the last section, I did this when I made everything have a width of 1, essentially. And then so that turns into essentially this formula, where C of k is chosen arbitrarily. So notation, this symbol is the integral symbol. So the symbol, this stuff is read as the integral from A to B of f of x dx, or sometimes as the integral from A to B of f of x with respect to x. So just like you can take derivatives with respect to different variables, you can do integrals as well. Okay. So the value of an integral of a function over any particular interval depends on the function and not the letter you use. So these are the dummy variables, essentially. You could do f of t dt, f of u du, f of x dx, as long as these variables match, f of t and dt, f of u du, f of x dx. So if you do like f of u dy, that's not going to work the same way. So the variable doesn't matter. That's just like in your calculator. It doesn't matter when you're graphing an equation if you have t's. Your calculator understands x's. So if you're out trying to graph 2t squared minus 1, you can type 2x squared minus 1. You'll get the same graph. Okay, so example 1, the interval from -1 to 3 is partitioned into n subintervals of equal length, blah, blah, blah. Let MFK denote the midpoint, express the limit as an integral. So integral symbol, we're going from -1 to 3. And then our function is just going to be x's. So 3x squared minus 2x plus 5 dx. Sometimes you'll see these stuff dropped in parentheses, sometimes not, just depends on the formatting. But that's the answer. That's the integral. Okay, definite integral and area. So if y equals f of x is non-negative, so it's always positive. So that's always positive, or 0 is a non-negative, doesn't mean it has to be positive, just means it can't be negative, so 0 would count. And integral over a closed interval, the area under the curve is the integral. So the integral actually calculates the area below a curve. So evaluate the integral from -2 to +2 of the square root of 4 minus x squared. So the first thing we need to do is look at the graph of the square root of 4 minus x squared. So graph square root of 4 minus x squared, and we get a lovely half circle. So this graph, whoops, there's 2 now. This is the half of a circle, so we're looking for this area. Now, we don't actually have to do any fancy math. That's a circle. The area of a circle is pi r squared. The radius of this circle is 2 units wide, so it is pi times 2 squared, or 4 pi. Now, that would be the area of the entire circle. I only have half of it, so I need to divide everything by 2, which gives me 2 pi. So the area below this curve between -2 on the x-axis and +2 from here to here is 2 pi. Okay, an integral function f of x is non-positive, or if it's non-positive, meaning it's 0 or negative, the non-zero terms are negatives of rectangular areas, so get negative values if the function is negative. For any integrable function, the total integral is equal to the area above the axis minus the area below the axis. Because they have negative areas, you take them away. Okay, so constant functions, if f of x equals c, where c is some constants, so a number or pi, things like that, on the interval from a to b, then this calculates out to this. Now, if you think about that graphically, if a function is equal to a constant c, that means it's a straight horizontal line. If here's a, here's b, integrating from a to b means you're just looking for the area of the rectangle. The height of the rectangle is c. The width of the rectangle is the difference between these two numbers. So this equation is essentially length times width, a rectangle. Okay, so example 3, a ship sails at a steady 7.5 nautical miles per hour, or knots, from 7 a.m. to 9, expresses total distance traveled as an integral. So we start at 7 until 9, it's traveling at a speed of 7.5. Variable doesn't matter, so we'll use x, why not? So it's the constant times the difference in the numbers. So 7.5 times 2, 15 nautical miles. Now, that is a very complicated way to do a very simple problem. You know how fast you're going, you can figure out how long you travel, which speed times, or distances, rate times time, 7.5 knots times 2 hours, you travel 15. Okay, so last thing here, accumulator functions. I think it's the last thing. The function f is integrable over the closed interval, and the definite integral from a to x. So now we have a variable at the top, not a number. X is variable. determines a new function for a less than x less than b, the accumulator function. So it looks like this. So example 4. Okay, so sorry for this goofy looking part of the notes, but I definitely did the example wrong the first time I did it. So after looking at it, I realized my mistake. So let's try this again. So if example 4 asks us, so it gives us let f of t equal 1 plus 2t for 1 less than equal t less than equal 6, and it asks us to write an accumulator function, a of x equals the integral from 1 to x of 1 plus 2t, dt, 1 less than equal t less than equal 6. So what we're looking at is, we've got some function that starts at 1, goes up to 6, and if you look at this equation, I can actually figure out what the values are at 1 and 6. So at 1, so this would be essentially f of 1, so would be 1 plus 2 times 1, or 3. So there's some point here at 1 comma 3. And then at 6, I can figure out the y value there as well, which is 1 plus 2 times 6, which is 13. So there's some point up here that's at 6 comma 13. And it draws a straight line connecting them. So the accumulator function is used to calculate the area below the curve. Now the issue is we're going up to x. So we're letting x slide. So our area is not going to be just a nice constant number. Now this shape we have here is actually a trapezoid. I'm going to draw it the way you normally used to see a trapezoid, where you have 2 parallel sides and 2 sides that are not parallel. Now, the trick we need to do is, so the area for a trapezoid is 1/2 the height, and then times the sum of the bases. Now you have to be careful because in this figure here, this height is actually this distance, okay? And the bases are actually here and here. So the figure got rotated 90 degrees clockwise. So I need to fill in these values. So the problem is they're going to be variables. The height, for example, is this edge. But this edge, the length of this side, is whatever x is minus 1. Now, the base, one of them's up here, the other one's down here. This one we know, because that's actually this edge. And x, we know what the height is there, is the far left side. This height is always 3. The problem is this edge over here, the other side, the B2, I don't know its measurement. It's 1 plus 2x. Because I'm letting x vary, so I don't know how long B2 is. B1 is stuck here. It's the 3 units tall. So this becomes 1/2 x minus 1, 4 plus 2x. Now, even though those are out of order, I'm actually going to distribute this 1/2 into the back set. As long as I only use it once, I'm allowed to do that. This will make my multiplication easier. Now, I could do a FOIL right away, but I'm going to make my math simpler. So 1/2 times 4 is 2. 1/2 times 1 is x. So I'm going to multiply these guys together. So now it's a FOIL. That's 2x. That's x squared. That's -2. That's -x. So in proper order, x squared plus x minus 2. So this is my accumulator function. Now, it will work, like the easiest way to check is to check this left edge. If you're at 1, you have not had time to accumulate anything yet, so the area should come out to be 0. And if I plug 1 into my equation, 1 plus 1 minus 2 is 0. If you plug 6 in, you should get what you would have if you had a trapezoid that had 1, 13, and 5 here, because you've accumulated the whole thing. So there is ways to check by actually drawing the trapezoid, figuring out the measurements, and checking them against this formula. But this is how actually example 4 should have been solved. Okay. Integrals on a calculator. So lots of calculators have some thing that will let you actually calculate given some bounds. On a Casio, you go to, in your regular menu, you go to Option, Calc, and it's this one, which in my case is that. So on a TI, you press the math menu, and I don't remember how far option it is, but it'll say FN int or something like that. Depending on your TI, the formatting looks a little bit different for the newer TIs and the newer Casios. In fact, actually, it'll actually give you the integral sign and put some boxes here that you can put numbers in, and then you would type your equation in, and then dx or whatever would show up. On older TIs, it'll say something like FN int, and then you would type your equation, comma x, comma the lower bound, comma the upper bound. On a Casio, it looks like this. You would type your equation, comma, lower bound, comma, upper bound. You don't need the x in there. Okay, so numerically, so for me, if I'm doing this first one, my equation is x sine x, comma, lower bound, -1, comma, upper bound, 2, close parentheses, enter. So this thing comes out to be 2.04. For this one, so integral of 4 over 1 plus x squared from 0 to 1, whoops, from 0 to 1 comes out to be 3.14, that's pi. And the last one, the integral of e to the negative x squared from 0 to 5. So this comes out to be 0.89. So now you have to be careful if your functions are discontinuous. So for example, this function down here, if you look at the graph, let's see here, the graph of this function breaks at 0. That would be 0 over 0 if you graph just absolute value of x over x. But otherwise it looks like this. But I'm going from -1 to 2, so I can just think of it in terms of the rectangles. There's one rectangle here that's 1 unit wide by 1 unit deep, so this rectangle has an area of 1. There's another rectangle over here that's 1 unit tall by 2 units wide. This rectangle has an area of 2. Now since this rectangle is below the axis, it has actually a negative area. So it's area above minus area below. So this whole thing is just equal to 1. So if you look at the graph, sometimes you can get now, we'll see what happens if we try to do this on the calculator. That option absolute value of x divided by x from -1 to 2. It did work this time. Some calculators won't calculate that because of this discontinuity. It'll give you an error. So if that happens, you may need to actually look at the physical graph of your function, which does bring us to the end of the section.